Today we're learning about conditional probability. The probability of event A occurring given that event B has already occurred is given by the notation probability of A given B. That little line in there means given. Okay, so what this means is given that B has to occur, what is the probability that A occurs? So there's two different types of formulas that we're going to be looking at here. The first box, the top box, is all in terms of probabilities. You can find the probability of A given B using the formula probability of A and B over probability of B. Now, it makes sense that if you find the probability of A given B, that the total of B is your denominator of that fraction. And it's the A and B, which is the overlapping section, that you put on the numerator. If you thought about it with your Venn diagram, with our two overlapping circles, if I was trying to find, or this overlapping part here would be A and B. If I was trying to find the probability of A given B, that is saying that of this B circle, so given this, the B circle, what's the probability of A? And the A part would only be this overlapping section. So it's the A and B over the total of B. Okay, it also works in reverse. If I want the probability of B given A, then it would be probability of A and B over the probability of A instead. So looking at that other circle. We can also write these formulas, and they look pretty much the same in this second box. Probability of A given B, and you can see the A and B with the little lines on the outside. Remember that those lines mean the number. It's the number of things in A and B over the number of things in B. Okay, so it's just a new type of notation that we have been using. Otherwise, those formulas are the same. One of them uses probabilities and one of them uses number. And what we're going to be looking at is independent events. Two events A and B are called independent if the probability of A is not affected by knowing whether or not B has occurred. In other words, we can prove that events are independent if the probability of A given B is just equal to the probability of A. And the second dot point there says if A is independent of B, then B is going to be independent of A. So let's have a look at our examples. A card is drawn at random from a standard pack of 52 cards. Find the probability that it is an 8, 9, 10, Jack or Queen if nothing more is known, meaning that there's no other restrictions placed on us at this point. So that means that we're looking at all 52 cards that are in our deck, and we just want to know how many of them are 8, 9s, 10s, Jacks or Queens. So that's 1, 2, 3, 4, 5 different types of cards. And in 4 suits, 5 times 4 means that there will be 20 of those. That simplifies down to be 5 out of 13. Question B. It is known to be a court card, which is a Jack, Queen, or a King. So I'm trying to find the probability of an 8, 9, 10, Jack, or Queen, given that I'm only looking at the Jacks, Queens, and Kings. So the Jacks, Queens, and Kings, the number of cards that are Jacks, Queens, and Kings, that makes my denominator. So there's 3 of those in each suit. 3 times 4 makes 12 for my denominator. Of the Jacks, Queens, and Kings, I want to know the probability of selecting 8s, 9s, 10s, Jacks, or Queens. So here is the Jacks and Queens again. Okay, so there's going to be 2 cards in there in each suit. So 2 times 4 makes 8. There is 8 Jacks and Queens out of all of the jack, queens, and kings. We're basically getting rid of the kings. So 8 out of 12, and that simplifies down to be 2 out of 3. Let's try another one. It is known to be an 8 or a 10. So I want the probability of 8, 9, 10, jack, queen, given that I've only got 8s and 10s. If I only have 8s and 10s that I'm using, there is 8 of those in the pack. So if I only have 8s and 10s, what is the probability that I'm going to draw an 8 or a 10? Well, given that I have all the 8s and all the 10s in here, I'm going to have 8 chances of getting an 8 or a 10 out of that. So 8 out of 8 means a probability of 1. Part D, it is known not to be a 2, 3, or a 2, 3, 4, or a 5. So I'm trying to find the probability of an 8, 9, 10, jack, queen, given that it is not a 2, 3, 4, or a 5. So starting with my denominator, if it's not a 2, 3, 4, or a 5, that's 16 cards that it cannot be. So if I take the 16 cards away from my 52, that means there's 36 cards that I do have that are not 2s, 3s, 4s, or 5s. So of all the other cards that I have, I want to find the probability of getting an 8, 9, 10, jack, or a queen. Now, a queen is not, sorry, not a queen. An 8 is not a 2, 3, 4, or a 5. A 9 is also not a 2, 3, 4, or 5. A 10 is not a 2, 3, 4, or 5. A queen is not a 2, 3, 4, or 5. And a jack. None of those things have been excluded from my deck that I'm using here. So all 5 of those, 5 times 4, means that there will be 20 cards that are favourable for getting an 8, 9, 10, jack, or queen out of the 36. It's really only the 6s and 7s that are in there that are not favourable outcomes. So simplifying that fraction down, we get a 5 out of a 9. Question 2. In a certain population, there is 45% of people that have blue eyes. So I'm going to write above here, population of blue, meaning for blue eyes. I'm going to write it as a decimal, would be 0.45. Okay, so that's this first bit of information. Then we have a 15% chance of blonde hair. So probability of blonde hair is going to be 0.15. And 15% have blue eyes and blonde hair. So that would be probability of blue and, meaning that little symbol there, blue and blonde is going to be equal to 0.15. So question A says find the probability that they have blonde hair given that they have blue eyes. So I'm trying to find the probability that they are blonde given that they have blue eyes. Now what we want to do is we want to try and adjust these formulas that we have up here that I've highlighted here in pink. The probability of A given B is A and B over probability of B. So for mine, if it is probability of blonde given blue, it's going to be probability of blonde and blue, or blue and blonde, over the probability of blue. So just adjusting the formula a little bit. So I know those numbers from the information I've been given. The probability of blue and blonde was 0.15, and the probability of blue was 0.45, and that simplifies to be 1 out of 3 chance. Part B, find the probability that they have blue eyes, so probability of blue, given, so line, that they have blonde hair. Okay, so we're going to adjust our formula here again. That's going to be the probability of blue and blonde over the probability of blonde. So, again, from our information on the top of the question, probability of blue and blonde was 0.15, and the probability of blonde is also 0.15. So that has a probability of 1. So the probability of blue eyes, given that they have blonde hair, will be all of them. Question 3, new question. 2 die are thrown one after the other, and we have 3 events that we want to look at here. Let A be the event that the first die is odd. Let B the event that the second die is a 1, 2, or 3, and C be the event that the sum is 5. I'm going to draw a little diagram to try and show what is going on here. So we have our first dice with the numbers 1, 2, 3, 4, 5, and 6. We have our second dice with the numbers 1, 2, 3, 4, 5, and 6. So what we want to do, I'm going to use some highlighters here. For A, let A be the event that the first dice is odd. So the first dice is odd would be anything in the column with the 1, the column with the 3, and the column with the 5. Okay, so that's event A. Event B is going to be the event that the second dice is a 1, 2, or 3. So that would be the second dice, anything in that row, or that row. And finally, the third event is that C is the event that the sum is 5. So a 4 and a 1 makes 5, a 2 and a 3 makes 5, 3 and 2 makes 5, and 4 and 1 makes 5. Now, I'm asking this question. It says, which of the 3 pairs of events are independent? To know if something is independent, back up here in our notes, events are independent if probability of A given B is equal to probability of A. Now we can obviously adjust. It doesn't have to always be A given B. It could be B given C would be equal to the probability of B. So we are going to find all that information so that we can use that formula to see which ones are independent. So first of all, I'm going to need the probability of A, the probability of B, and the probability of C. So the probability of A was the event that the first dice is odd. So the first dice is odd is the pink arrows that I've got there. So there's 6 numbers, 6 there that have 1 involved, then another 6 with the 3, and another 6 with the 5. So that is a total of 18 numbers out of the 36 total options, which is a probability of a half. The probability of B was the event that the second dice was a 1, 2, or a 3. So that's going to be the 3 horizontal rows going across from the green lines there. So all of row 1, 2, and 3. So again, that's going to be 18 out of the 36, which simplifies to a half. And option C is the event that the sum is 5. So they're the ones that I've highlighted yellow there. There is 4 out of the 36 that have a sum of 5, which simplifies to 1 out of 9. To use that formula for independent, I also need to know the probability of A and B, and I'm going to need to find all of them. I could do A and C, and the other one would be B and C. Just the 3 different combinations of using those 3 letters. So the probability of A and B, and meaning it has to have both things. If A is the first one being odd, and B is the second dice has a 1, 2, or 3, I am wanting this one, and this one, because it has both criteria, that one, and that one, that one, and that one. So there is 9 out of the 36 that has both A and B. So that is simplifies to a quarter. A and C means it has to be both in the pink rows and it has to also be highlighted yellow. So that is just going to be this one and this one. They're the only ones that overlap for those. So it's 2 out of the 36, which simplifies to be a 1 out of 18. And the probability of B and C means I want the green and the yellow, which would be, trying to find a different color to use here. We could have the green and the yellow would meet at that one, and this one. There's 3 times out of 36, which simplifies to 1 out of 12. So now that I've done all the background work, I now need to test the independence. Okay, so I've got to test all 3 possibilities here. A given B, I need to test probability of A given C and probability of B given C. So I need to modify my formulas a bit. If I want to find the probability of A given B, using the formulas from the previous page, that's going to be the probability of A and B over the probability of B. Now we've just worked out these things. The probability of A and B was a quarter, and the probability of B was a half. A quarter divided by a half is a half, and in order for it to be independent, the probability of A given B needs to be equal to the probability of A. The probability of A up here is indeed equal to a half. So that means, therefore, that A and B are independent. Okay, let's try the next one. Probability of A given C. That's going to be the probability of A and C over probability of C. So probability of A and C we worked out was 1 over 18. And the probability of C was 1 over 9. That also equals a half, which is also equal to the probability of A. So that means that A and C are independent. And finally, probability of B given C would be the probability of B and C over probability of C. So probability of B and C is 1 out of 12. Probability of C is 1 out of 9. And when you divide them, you get 3 over 4. Now, in order for this to be independent, this needs to be equal to the probability of B. But the probability of B is equal to a half. So this is not equal, to put the line through that equal sign, and that means that B and C are not independent. Okay, question 4. Sarah and Maya can't agree which movie to watch, so they play a game throwing 2 dice. If the sum is a 7 or an 8, Sarah chooses the movie. If the sum is a 9, 10, 11, or 12, Maya chooses the movie. If the sum is less than 7, they throw the dice again. So here we want to draw up another table showing our possible outcomes. So our first dice, our second, and the numbers 1, 2, 3, 4, 5, and 6. So the important thing to realize with this question is if they roll a number less than 7, they basically disregard the result and they start again. So although there are 36 outcomes, a sum of less than 7 will be discarded. Hence, these outcomes will not be included. So instead of having all 36 outcomes, we only want the ones that are 7 and higher. So 1 plus 6 makes 7. All the 7s are going to go on this diagonal across here. And then these will be the 8s, 9s, 10s, 11, and 12. All the ones that I haven't filled in are going to be discarded. So the probability that Sarah will win the movie choice, she will win if she gets a 7 or an 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There is 11 7s and 8s out of the total of, we need to add on all the rest of them, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 11 out of 21. The probability that Maya will win, she will win if she gets a 9, 10, 11, or 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. She has 10 out of 21 outcomes that would let her win. So it is very, very close, but Sarah has just slightly higher chance of winning and choosing the movie. So therefore, Sarah has the higher chance of choosing the movie. Okay, so that's it for the examples on conditional probability. You need to work on exercise 12G.